Lunch. Our next speaker is Miguel A. Calles, speaking on costly findings in serverless computing. Please give him a warm welcome.
Thanks for having me here. So I've been working in serverless computing for about 5 years now, and I just wanted to share some lessons learned. By the term costly, I don't mean necessarily dollars or how much it was expensive. It could have meant difficulties in troubleshooting, difficulties in architecture, just pain points that I've discovered over the years. There are many more, but these are the ones that have kind of stood out to me over the past few years. And just wanted to share those. I'm just curious, how many of you are familiar with serverless computing? Awesome. Well, for the rest of you, I'll give a brief overview on what it is and how they're typically used, and then I'll jump into some of my lessons learned. So what is serverless? There's many definitions out there. Really what it comes down to is you have an on-demand service. Instead of having a dedicated provisioned server with 2 gigabytes of RAM, 4 CPUs, 250 gigabytes of disk space, it's really, the service is there, you use as much as you need, you pay for as much as you need. So there's no dedicated servers, and they provide compute, database, and storage. So it's really just pay as you go. So here's some examples of the types of serverless services you'll find out there. There's compute or functions for code execution. There's application programming interface like API gateways, API management, databases, object storage. Object storage is really just like file storage. Like you can store anything. It can be an image, a JSON file, a document. Orchestration, so there's a way of putting all these things together. So there's serverless services that help you put your functions in a specific business logic. Continuous integration and continuous delivery, so pipelines, how you deploy your code, how you deliver your code, how you test it. And artificial intelligence and machine learning. So if you have data, you can set up a serverless process to analyze that and come up with meaningful conclusions. So there's many out there. These are the ones that I'm mostly familiar with Amazon Web Services. I've used Azure a bit, Google Cloud. I've been, over the past several months, getting more familiar with the Cloudflare and Workers and Pages platform, and these are many others that are available. So you may be wondering why you want to use serverless. So there's a lot of reasons. You can deploy your code rapidly instead of focusing on provisioning, configuring, maintaining, hardening your server. You just upload code and run it. There's typically less infrastructure involved, less maintenance. By maintenance, it means like keeping your servers patched, keeping it hardened, addressing the latest threats out there. It potentially have lower costs as well. I've worked on some projects where I've only paid 5 cents a month for web hosting and all the data storage and all that. So it can be really cost effective. And there's some debate out there, but I believe serverless can also provide you with smaller attack surfaces, depending on how you've architected your application. It can be really helpful, especially since a server, you can have a dedicated IP and you may not have all the ports locked down. With serverless, you don't necessarily have to worry about those kinds of things. So just kind of walk through a typical AWS architecture that I work with on AWS. So over here, we're going to have 2 types of clients, a web application and a mobile application. The web application has a stack here that's meant for the website, all using serverless services or services that integrate well with serverless. So we use the Route 53 service here and the CloudFront service to get us a content delivery network. So Route 53 does the DNS over here. And we put all our website files as objects in a bucket. So that's object storage. So when the web application goes to mywebapp.com, Route 53 will resolve the DNS, route it to our CDN. The CDN will then read the files from the object storage and deliver that to the client. If our web application will also need a backend, so rather than a server, we can do that serverless as well, where we can set up an API gateway. That's API management. We define our endpoints, the HTTP methods that are allowed to work. We can use the open API specifications to automatically configure our API gateway. And so when the mobile app or the web app does an HTTP request, it will go to the API gateway. The API gateway will then validate if it's a valid request, forward that request to a Lambda function, which processes the event and returns a response. If it needs to, it can talk to a serverless database and read, write, put, update, delete data as necessary. So hopefully this gives you a flavor of how you could use serverless and an architecture that is very common. So here's some lessons I've learned. Up until just recently, OWASP had input injection as the top risk. It's still that in the serverless top 10. The latest 2023 that draft of the OWASP top 10 has broken object level authorization as the highest risk, meaning if I go and ask for data, the API will give it to me. And then if I say, oh, my name's Bill, give me that data, and it'll give it to me even though I'm logged in as Miguel. So that's broken object level. I'm not meant to get that data. So that seems like an appropriate higher risk than input injection. But it's still pretty high up there. So in this scenario, we architected our Lambda function to get an update from the database. So anytime something data was written to the database, it would send an event to our Lambda function. Our Lambda function would then look at the event and say, oh, something's been written to the database. We're going to clear our API gateway. So the reason we did this is the type of data that was written to this database isn't updated very often, and our API was caching it to make it more performant. So rather than reading from the database all the time, we'll just cache it at the API gateway so the gateway can respond just like that. And whenever we did update the database, and we'll tell the gateway, okay, there's new data there, go clear it. We found, though, that there was a kind of an injection attack, per se, where the database was sending events to our Lambda function that were old. Some of them were days old. And so it was sending false triggers to the Lambda function. Anytime the Lambda function got an event, like, oh, it must be new, let's clear the gateway, cache. So to remediate that, we did input validation, which is something we should all do in our code, and look at to see if it's a valid event. It's 5 minutes or less. And if it is, then okay, let's move on to the next step. We don't want to overwhelm the gateway because we could have gotten a blast of updates all within 5 minutes. So we'll just do it once every 5 minutes. So here's an example of how painful it was. So what ended up happening was when the API gateway got too many cache clear requests, it stopped working. We got a denial of service, so self-inflicted denial of service attack. So input injection can result in a lot of risks. That's why it's in the top 10 still for OWASP. So we want to update, make sure we update our code to validate all inputs, do safe deserialization, that's a hard word, deserialization, and regular expressions. Some libraries out there do not deserialize very safely and can result in injection attacks. We'll cover this next, but use least privileged code, meaning you don't give more permissions than it needs to, and use software and try-catch blocks to help you with writing better code. So the next one is, if we have our functions, our code to be overprivileged, some really bad things can happen if there is an attack. So in this example, we had a function with a permission using the AWS Identity and Access Management service, and was pretty much set to admin privileges. It can do any action, there's a star there, and there's a resources star, so it can do any action on any resource on the AWS cloud. I did this intentionally just to see what you could do wrong. So I wrote a function that was vulnerable to injection attack, and this function was designed to just get data from a database. I did the injection attack, and I was able to talk to the Identity and Access Management service on AWS, and I can change passwords, delete privileges, assign privileges, really nasty stuff. I read this really interesting article on medium.com where the security research did a server-side request forgery request and sent a fake file up there and was able to escalate privileges and do an AWS account takeover attack. So really bad things can happen if we overprivilege our functions. So the solution was to limit the function to only do what it's meant to do. So we went here, we give it a read database permission. It can talk to the DynamoDB service on AWS, do a query, and it can only talk to the table name table in a specific region for a specific account. So if anything does slip through, like an injection attack, malicious payload, and it tries to talk to our IAM service and do an account takeover, it should fail. So here's some interesting things that I found. There's a few frameworks out there for working with serverless. One of the most popular ones is called the Serverless framework. And the way it was originally designed was to have a default role for the privileges. And what ended up happening was developers would just update the default role, and every function got every other function's permissions. So the best case to do is to put the extra effort and write one role for every function. And there's a newer framework out there that AWS provides, their Cloud Development Kit, and they have some of these lessons learned baked in there, and every time you create a function or resource in the AWS cloud, it has the least privilege by default. Oh, and if you're working with IAM keys or tokens to get access to AWS, rather than having them be access keys that live on forever, if you can use these temporary tokens that expire after an hour, it reduces the time that you're vulnerable. All right, so here's an interesting one with rate limiting. We added authentication to a mobile app where the user would sign up with their phone, they get a 6-digit code, and they punch in that 6-digit code, and that's how they're authenticated. No password, right? It's really common, right? Well, as part of our cybersecurity requirements, we hired penetration testers, and one of the findings they gave us was we were able to crack that 6-digit code by sending 1 million requests in under a few minutes, and just brute force attack it. So we had to make some changes to that. We implemented rate limiting, where in the API gateway, we gave it some specifications that only a certain amount of API requests are allowed. And then when it goes through the logic to check if it's a valid code, it will, if the code is not correct, at least for this implementation, we sent a brand new code. So it was always a moving target. And after so many attempts, failed attempts, then the user was locked out for a temporary period where they couldn't try any more codes going forward. There's various ways. Make sure you have good business logic in there. You can use a web application firewall to help protect against brute forcing, bots. Rate limiting and lockouts were appropriate for us to meet our cybersecurity requirements and make sure we passed the penetration test the next time we did it. And also, if you monitor the usage, you can also get an indicator of something's wrong if you get a spike in usage, increased number of errors. So here's another one, over provisioning, where specifically with our Lambda function service and DynamoDB tables, our developers just wanted to build as fast as they could, so they set a standard 2 GB CPU size for every function with a 30-second timeout. That was the maximum timeout you could give it before the API gateway stopped responding. And the database, okay, well, we're going to give it flat 20 write capacity and 20 read capacity. It works. Why change it? Well, we ended up finding that it got kind of expensive, and we're paying a lot of money. I'll show later on how making these changes actually helped improve our costs. So one thing we did to make sure our system was as performant as possible with the best cost, we went through every function. We understood its CPU usage, how much time it typically took to execute, and we adjusted the CPU usage and the timeout based on what it actually did. Sometimes it made more sense to pay for more CPU because the code could execute faster and timeout would finish, let's say, within one second. But if we gave it the lowest CPU, which was cheaper, ended up taking 10 seconds, and that would affect our performance. So we did those kind of engineering analysis and resized our functions. We also took advantage of the on-demand capability that DynamoDB has. On-demand was 10 times more expensive to write data than it was through provision capacity, but we were finding that our traffic was really spiky. We would get a lot of writes and then would be idle for a long time. It wasn't a steady stream of reading and writing data. So rather than paying for more expensive provision capacity, well, we might as well pay 10 times more if it's only for a few minutes every hour. So we found that to be a lot more helpful. And it also gave us ability to scale, because sometimes the 20 read-write capacity could be exceeded if we had a lot of users using the system at any given point. So if it was on demand, we'll pay a lot when we need it the most, and we'll hardly pay anything when it's idle. So just to reiterate, we sized our functions to how that worked, to the right compute size, the right timeouts. We also did an assessment of how many instances of that function we needed. So if we needed, we found that it was executed on average 10 times concurrently, then we would increase how many times the function could be executed concurrently. And we updated our database provision to make sense. If we had steady read-write, we would just pay for provisioning. So one time our mobile app went down and we could not figure out why. We had failed to monitor our services. We had no observability. So we started looking at this, looking for 500 errors. Uh, uh, Essentially, any HTTP code that was not 200 in the 200 range, and see when our services were down, because AWS does go down in certain regions or it's in degraded state. I've seen Azure down in all regions for all services twice in the past 3 years. So cloud is great. It just like any other system, it can go down. So it's good to monitor our applications, our services, make sure that they're functioning correctly. Another mitigation is to use multi-region and multi-cloud. So by multi-region means you can have part of your database and functions and all your services running in one part of in America, and then maybe have it running in Europe, different parts, so that if one region is completely down, you can fail over to another region in the AWS cloud, for example. Or you could leverage Google Cloud and Azure as kind of a backup, so that if it is degraded and you detect it fast enough, you can start doing like a degraded lower end version of your system in this other cloud, so that your application can stay functional. Oh, and this is a nice little trick. Leverage local storage on the clients. So if rather than always doing an API call from the mobile app or the web app, if the data doesn't change at all or it's specific to that user, just save it to the local storage, so that if there is an outage, some of that data is already there at the application, and the user may not even notice as much. So I mentioned earlier that we did an assessment of how our application runs and made some adjustments. So we call that a cost engineering effort. We found we were paying a lot of money to run our application, and we were wondering, well, how can we bring this cost down? So we started looking into optimizing how our compute was being done, optimizing our data usage. Sometimes we also found similar services that kind of did the same thing, that offered kind of a cheaper or less sophisticated solution, but it was good enough for what we needed. So sometimes moving to that allowed us to essentially build the same product with hardly or very not as noticeable change in the performance, and we got really great cost benefit from that. So when we started that in July, about a few years ago, right away, just within a month of starting the cost engineering, we were more than 50% cost savings. And after a few months of analyzing our application and making these changes, we had saved 98% of our cost. So meaning we were paying a lot of money for the time when our application was idle. So one way to assess if your application is designed to be cost effective is while you're in development, is try to break it, stress it, put a lot of load on it, write a lot of data, pretend there's a lot of end users. There's great tools out there, and you'll see the cost spike right away. And if that's the cost spike is more than what you thought when you were designing the system it would be, then you can catch a lot of these things in development before they go in production. So more recently, I've been working with Encryption. So AWS has this really nice service called the Key Management Service, and they allow you to use the keys they manage or you could use a customer managed key, which is specific to your AWS account. So with the AWS managed key, the AWS team controls that key, and their team has access to it, and they follow their security principles. But the customer, meaning me using the AWS cloud, can never access it. I just have to rely that they're doing it well. Well, if I want greater control, I can upload my own key, or I could create a key using their key management service. And in theory, only I can access it, and the AWS team should not be able to. Well, this seemed like a great idea. Well, okay, well, I want greater control. I want to make sure everything's encrypted. Let's move on that. The thing I failed to think about initially was, well, what were my requirements? Did I need to move to more control, or was AWS managing really good enough? Well, for the projects that we were working on, there was no need or requirements driving us to have that customer managed key. So what I found that when I had the KMS, the customer managed key turned on, I noticed my costs started going up. And I could not figure out why. We had just finished a project, and we were waiting for our users to arrive. We were waiting for some contracts to come in so we can, getting some production usage. And the bill was more than I expected for it being idle. I was like, okay, what's going on here? And so I looked at when the costs started going up and realized, oh, that's around the time I turned on this encryption with the customer managed key. After digging in some more, I found that it had costs. So when I switched away from the customer managed key in our development, I just had AWS manage it. I noticed that there were no costs. So anytime we have to work with our data, it needs to get decrypted and encrypted. And with the customer managed key, AWS charges you that. So we moved away from that in these projects because there was no requirement driving us to a customer managed key. So really, the lesson I learned there more recently was encryption is great. We should use it, but use it to what makes sense. Look at your requirements, see what you're actually required to do, and if AWS managing it is good enough to pass a requirement, an audit, then go with that. But if you need that extra level of security, then enable the higher end versions of encryption and incur those costs. So this will be the last lesson I cover. So you might have heard of spaghetti code, where just things are calling it, and if you were to draw out how the functions and the code's calling it, it looks like someone just threw spaghetti on the wall, right? Well, that kind of that can actually happen in serverless computing if a team's not careful in designing their system. So here, we were really gung-ho about microservices. They were kind of new at the time, and it seemed like it was the solution to fix everything. Everything's a microservice. Whenever we need data from the users, you go to the users microservice, and whenever we need data for this other type of data, we'll go to that microservice. Seems great, right? Well, we ended up finding that sometimes it was a little more complicated than we needed it to be. So in this example, we had our mobile app talking through the API gateway. And based on the sensitivity of our data, we had a public microservice for less sensitive data. And then we had a private microservice for our more sensitive data. And rather than having the private microservice exposed on the internet through an API gateway, we decided for this project it could only be accessed directly through an API call within your own AWS account. So how it worked was our mobile app talked to the API gateway, and our API gateway redirected that HTTP event to our Lambda function. Then our Lambda function said, oh, well, I need data from this public microservice. I'm going to make an HTTP call to the microservices API gateway. And then it would then redirect it to the Lambda function. That microservice Lambda function said, oh, I need access to more sensitive data. I'm going to call the private microservice. Well, given how we designed it, then this Lambda function would have to then call that Lambda function for it to get the data. This one would wait until this one was done, then send the response back. And throughout this entire process, this function is still waiting to get the answer. So it has to go through all these steps, send the data back, and then eventually send the response back to our mobile app, hoping it hasn't timed out after 30 seconds. So imagine your system has a bunch of these all over the place. If you can imagine, it might look like spaghetti if you were to draw it out. So what do? Well, we kissed it. We kept it super simple. We found that the security with the Lambda service was secure enough where this Lambda function can talk directly to this table. We apply some of the lessons learned we talked earlier with least privilege, execution, so forth and so on. You can even put this on a private, virtual private cloud, and then just have it send the data back. Much easier to follow, much easier to troubleshoot, less delays, less cost. It's just much simpler. So sometimes less is more. Microservices are great. They're not a silver bullet. Neither is serverless, by the way. So if microservice makes sense, I like to use them for public APIs for customers, where customers need to have a specific defined API. But anything internal, if you can do a direct call to a database, go with it. Simpler. And and you can use observability tools to help you see how your system works. If you give it the permissions on AWS, it'll start drawing out your environment, and it'll give you a graph, a visualization of how everything's working. And if it looks like spaghetti, then maybe it's time to go back and rethink the design. I just wanted to share some resources if you're looking to grow in your serverless knowledge, and for those of you interested in learning more about serverless, OWASP has their top 10, the Cloud Security Alliance has their list. There's many good serverless best practice blog posts. There's books. I rely a lot on the cloud provider documentation. I think it's really good. And I've learned over the past few years that if you just search awesome and whatever it is that you want to learn, there's really cool GitHub repos out there. So for this one, I just searched awesome serverless, and it gave me this GitHub repo with all these resources out there. So I just want to say thank you for having me here. I hope you found this talk interesting. Here's several ways to get in touch with me. If you're interested in learning about the security side of serverless, I have a book. And if you want to get hands-on practice on developing a serverless application using the AWS Cloud Development Kit, I've just started writing an ebook. I'm releasing it a chapter at a time. It'll be on medium.com right here. So with that, are there many questions? All right, well, I'll give you 25 minutes of your time back. Thank you so much.